You're on air.
You're live? Okay, so I'll start then. I'll just start on the integration.
Start it. Yeah, just do it.
Okay, cool. Right. So let's talk about the topic of integration. So before we were just doing, well, I didn't do it, but you're talking about differentiation, basic differentiation stuff. Um, Integration stems from something called, well, first we've got to talk about something really important called the fundamental theorem of calculus. And what that is, I'll just write down of calculus. I'll just abbreviate this. That is that integration is the opposite, is the inverse process. So you could, I don't know, you could, integration you can think of as an operation. So you can say integration is the inverse process of differentiation. Okay, that's sort of how integration is defined. And why is that true? I might spell that wrong. Why is that true? Well, if we just think about, we've got some function like this, and it's called f of x. And let's imagine we're at some x value of a. No, let's just call it, this is the x-axis. Yeah, we'll just say we're at some value of x. And let's say there is a function, and what it does is this function, a of x, a because it stands for area, this function tells you what the area under the curve is, maybe between x and 0. That's what a of x could do. Let's say there is a function called a of x that does this, all right? What are some of the properties of a of x? Well, if we increase x by a little bit, so we're at a new point now, and this is x plus dx, so the difference between these 2 points is dx. If we increase x by a little bit, then what is the resulting change in the area? We'll just call this new area now dA, right? So all we've done is we've said, what if there's a function called f of x? Let's imagine there's also a function a of x, which relates to f of x. And all a of x does is when you plug in an x value, a of x tells you what's the area under f of x, okay? We don't know if this function exists yet, but we're just going to imagine if it did, what would its properties be, okay? So we're at some value, a of x. We increase x to a little bit, x plus dx, and there will be a change in area, okay? And to a rough approximation, dA, the change in area, will be f of x. F of x is this height here, right? Because if I take x, I take f of x, that gives me this value. So the height here is f of x. The change in area will roughly be f of x times by dx, right? F of x times by this distance, that will be this change in area, which implies that dA divided by dx equals f of x. So what we figured out that if there was a function that gave us the area below some value x, then its derivative would be the function in itself. So we can define an inverse process called integration. And this inverse process gives us a. So we int dx, and that gives us a. So that sort of defines integration. That's where integration comes from, okay? And integration is really hard. In general, it's really difficult. Differentiation is really, really easy. The definition we have of differentiation, so for differentiation, just for you to remember, dy by dx is defined as the limit as h tends to 0 of this thing, x plus h minus y of x all over h. So it's defined as what this thing tends to as h goes to 0. And in general, it's really, really easy to evaluate this. What's not easy is to do the inverse process. So if we're given a function, it's really hard to find the one that differentiates back into it in general. It's quite easy with ax to the n, right? We just have to think about, oh, what's the inverse process? Well, we know that in general, if we want to differentiate x to the n, that equals multiply by the power, and then we take one off the power. So we know this process, and then figuring out the inverse is quite easy to see that if we have an n plus 1 up here, and we divide by n plus 1, when we differentiate, we're going to be multiplying this by n plus 1, so this is going to cancel, and then we take one off the power, which gives us the n we started with. So it's quite easy for polynomials, but in general, when we get harder and harder functions, it becomes really, really difficult to integrate them. So for example, one function that's kind of easy to differentiate, but really, really easy to, it's quite easy to differentiate, but really, really hard to integrate, would be an example of something maybe like 1 plus x squared multiplied by 1 plus x to the, let's say, 2015, okay? So if you wanted to integrate this, it would be an absolute nightmare. If you want to differentiate it, you can just use the product rule, and it would be quite easy, okay? So some of the things you want to remember when you're doing integration is you really want to remember how to integrate polynomials. This is sort of your bread and butter. And exponentials are kind of easy to integrate as well, because we know when you differentiate an exponential, you're always going to get a term. You're always going to keep the exponential term, and then you just need to do the chain rule on this bit in here. And then remembering that if you differentiate minus cosine gives you sine, means that obviously if you integrate sine, it gives you minus cosine. You just need to remember sort of to divide by these factors, the factors that come out when you do the chain rule. So again, if we differentiate just argument, we would get just a, because the derivative of this is just a. So you need to be dividing by the argument every time. Integration, you tend to see a lot more dividing by the arguments just to make sure it turns out to be the same thing, okay? So integration is harder, but as long as you remember some of these more general results, it's not too bad. Okay, so integration by substitution. So there's quite a lot of methods to integrate stuff, seeing as integration is so hard. And one of them is to change the variables, okay? So for example, say we were integrating this 1 plus x squared times 1 plus x to the 2015. We're integrating this with respect to x. Maybe we might try saying, how about if we make the substitution, we'll say u equals 1 over x, right? We might try something like this. And then the next thing to do is we need to replace every single thing in this integral by the corresponding term in u, okay? So we might try differentiating this and say du equals minus 1 over x squared. So we've just multiplied by the power is minus 1. We take 1 off the power, so we get x squared, multiplied by dx. And then 1 over x squared is the same as 1 over u squared. Sorry, it's the same as u squared. So this is the same as minus u squared dx. And rearranging, we see 1 over u squared du minus equals dx. So now in this integral, we can place the dx with this, and we can also replace all the x squareds with u's, and this might make the integral even easier to do. It turns out that this is the way you would actually do this integral. I'm not going to go through it completely because it's quite a complicated one, but we see that by making substitutions, we can make things slightly easier. Right, yeah, so yeah, that pretty much is just what this little paragraph says. And then here's an example. They've got y equals sine cubed 2x, cos cubed 2x. This would classically be something that's really, really hard to integrate. But if you make the substitution, it tells you here, and a lot of the times in your A-level questions, it's going to tell you the substitution to make. It makes things quite a lot easier. So if u equals sine of 2x, then this y just turns into sine of 2x cubed, so u cubed, cos cubed. Well, it probably turns out that when you find the dx, so okay, if u equals sine of 2x, then what does du equal? Well, it equals the derivative of this, sine x differentiates to cos x, and then we need to multiply by 2 dx. Okay, so now when we see a dx in the equation, we can replace it with this. And I'm sure he does that here. Yeah, so he says du by dx equals 2 cos 2x. And then you'll see that when you apply these substitutions, the integral will magically become a lot more simpler. And you end up with something like this to integrate with respect to u, which makes it much easier. Okay, so I think for most of your A-level questions, they're going to give you the substitution to make. Integration is really difficult if you don't know what substitution to make. So when they actually give you things, they make things a lot easier. The one time they probably won't give you the substitution is when you have things like you want to integrate something 1 over the square root of a squared minus x squared dx. Things like this. But there might be a plus sign here, there might be a minus sign here, there might be a minus sign in front of the a. But luckily, I think in your formula booklets, they give you a lot of the results, the standard results. So they might have the corresponding integral here. They might say, if you have this, it'll be in the formula booklet. It might tell you that a good substitution to make would be try x equals sine of theta. That might be a good substitution to make. And you can sort of see, sorry, a sine theta times a. And you can sort of see why this might be a good substitution to make, because if we put x equals sine theta times a in the bottom bit, so just to see what does this become? That becomes a squared minus x squared, which is a squared sine squared theta, we can factor out the a's to just get an a, square root of 1 minus sine squared theta. So you can already see why this might be a good substitution, because the square root of 1 minus sine squared theta, that's just cos theta. Right, because cos squared theta plus sine squared theta equals 1. Okay, and it just so happens that when you take the dx of this, you get sine theta cos theta multiplied by a. So you can see we'd get a cos theta on the bottom and a cos theta on the top. Sorry, I need a d theta here. Okay, so when you have the square root of a squared plus whatever, oh, and there's another one if you have the square root, if you have 1 over a squared plus x squared, things like this. And here you'd actually make a tan substitution, because you remember if 1 plus tan squared equals, I think, cos squared or something stupid like that. So yeah, just to say that they might not give you the substitutions for these sort of integrals, but they'll be in your formula booklet. Or you should just remember that when you have square roots, it's a good idea to use sine or cos, and then when you don't have them, it's a good idea to use a tan substitution. Okay. Okay, cool. So yeah, that's one method of solving integrals, is just to make substitutions. Another thing to remember is that if you integrate a derivative of some function divided by the original function, then that is just ln of f of x plus k. Oh, one thing I haven't talked about actually is this plus constant term, okay? So in general, if you integrate something like this, you need to add on a plus c to the thing that you would have differentiated to get it. And that is because, obviously, when you differentiate a constant term, it goes to 0. So if you want to be the most general thing, remember, integration is the opposite of differentiation. If you want to be, what is the most general thing that would have differentiated to get this function, you need this constant term, because the constant term could have been there before. And geometrically, this is kind of easy to think about, because if you have some function, and you want to find the area, wait, so let me think of what's the best way to explain this. So we said we had some function a of x, which gives you the area at some point x, and then we said that df by dx equals the area of x. So if you differentiate this function, then that gives you the area. You can't really tell here because I've already drawn where the intercept on the graph is. Okay, don't worry about the geometrical interpretation. Just remember that the most general thing, when we integrate something, we need to find the most general thing that differentiates to it. So we always need to add on a constant term, because the constant term does go away when we differentiate this. You can actually get rid of the constant term when what I've drawn here, I've drawn the graph, I've shown you what the intercept is. So if you know what the intercept of the function is, then you can get rid of the constant term. And also when you integrate between limits, so here this is just a general integration, but if I say I wanted the function, I wanted to integrate sine of x between 0 and pi over 2, I'm not going to get a constant term here. This would integrate to some function plus a constant term, and I need to evaluate it between these two limits. So I would end up with something like, whatever this integrates to, it would be a cos, but I've just left it here in general, and be this plus c minus f of 0, and then minus c. So you see these constant terms are always going to cancel if you have definite limits. You're going to get a plus term and a minus term. So in general, when you have limits that you know, the constant terms don't matter. But if you don't have limits, if you're just writing a general function being integrated equals big f of x, then you need a plus c, okay? Because of the way derivatives work, they get rid of constant terms. Okay, so if we're integrating the derivative of something divided by the original function, then this equals natural log of the modulus of the function plus this constant term. Why is that true? Well, again, if we just differentiate this, so d by dx, the constant term goes away, which is good. What's the derivative of this? Well, using the chain rule, that's the same as 1 over f of x multiplied by, we need to differentiate this, okay? Which is the original thing we started off with. So anytime you see something like maybe x squared plus 3x, and if on the top you have this, You need to spot that, oh, look, this is the derivative of the thing below. And these integrals, in general, if you see like a really, really complicated polynomial thing, it probably turns out at this level, when you're integrating it, that the top will just be the derivative of the bottom. And try not to get caught out by that. If you see something that looks really daunting, you want to check, oh, what happens if I differentiate the bottom? Does that equal the top, the numerator? So if I differentiate the denominator, if that equals the numerator, then it makes it really, really easy, because then I can just say this, plus C, okay? So that's a useful trick to remember. And then here's an example of this. Oh yeah, to be careful, if they factor things like this, they're trying to make it more complicated than it is. You might want to expand out the fraction and see that this is 2x, 2x cubed minus x squared. Actually, no, this is a partial fraction example. So, sorry, this doesn't have anything to do with the derivative thing I was just saying. This is just saying that if you have something quite complicated in the numerator and the denominator, a good way to do it is to use what we know from partial fractions. So to split this up into these terms, which are much easier to integrate, then you can get your answer that way. So that's quite nice. Okay, this is probably the most important way of integrating things: integration by parts. So this is the formula for it, but where does it come from? So if we think about the product rule, so what's the product rule? Say we have some function u of x, and another function v of x, right? What happens when we differentiate this function? So u of x, v of x. If we differentiate that, we will get the derivative of u. I've stopped putting in the x's here because I think at this point it's probably quite obvious that u is a function of x. And we need to add on the derivative of v times u. Okay, right. What would happen if we then integrated both sides of this equation now? So if we integrate both sides, we get the integral of a derivative, Don't forget the dx. If you ever do this proof or whatnot, if you ever integrate both sides of an equation, don't forget to put the dx. A lot of people forget that, and it's just not correct. I think I'm going to swap the order of these. That's obviously fine. They commute with each other. Just to make it more apparent, so I'll put the u here first, dv by dx. Okay, so we're integrating something which is a derivative, and because integration is it's essentially defined, or is in via the fundamental theorem of calculus, integration is the opposite of differentiation. So if we integrate a derivative, we're just going to end up with the thing we started with. So we get u of x times a v of x, and that equals the integral of u dv by dx times dx plus the integral of v du by dx. I've stopped the order again. Okay, but we can see that this is essentially the same thing. The only step I need to do now is I need to just put everything on the right side, equals uv minus the integral of du by dx v dx. Okay, so it comes from the product rule, and here they've put in limits. So they've started off. This is the formula I've derived. If you put in limits, okay. So obviously for the integrals, the actual integrals themselves, if you integrate from a to b, it's pretty obvious that you should do this. What's not so obvious is you also need to put limits in around this function, right? Which is the same thing as saying that if you integrate this from a to b, then that's evaluating the function at b, and then taking away the function evaluated at a. Okay, which makes sense, right? So let's imagine, this is just how sort of derivatives integrals are defined, right? So if you integrate something between a and b, and it's the derivative, well, first you'd integrate this to get this function, and then you'd need to do that between the limits. Okay, so basically all I want to say is don't forget to put on these limits on this part. It doesn't look like it should need them because it's not an integral, but remember that you did integrate this during the proof. Okay, so you can't forget to put this b and a here. Right, a nice way of thinking about integration by parts is, if you can't really remember that formula, is that it's a way of moving the derivative over. So you have two things being multiplied together in an integrand, and say this is really, really hard to integrate. But if you notice that if the derivative was applied to this function and not this function, so if you look at the difference between these two things, it's like the d by dx has been moved from the v onto the u, right? That's what it looks like's happened, but you've also got this extra term. Maybe this function is a lot easier to integrate. So an example of that would be if you want to integrate ln of x, natural log of x, okay? So natural log of x is the same as saying, sorry, I want to put this in a different order. So if you want to differentiate the natural log of x, you could imagine that that's the same as saying 1 times the natural log of x dx. Right, so we know that if you differentiate 1 over x, that gives you the natural log of x. Technically, there's a modulus sign, but let's not worry about that. Let's not go too far into the weeds. But if we differentiate, sorry, I've done this the wrong way around. If we differentiate, that doesn't look right at all. And I'll get rid of this. If we differentiate the log of x, that gives us 1 over x. Okay? So we can imagine that we already have the d by d. Sorry, I want to make this one right. Yeah, we can imagine that we already. I've done this in the wrong order. Let me just move this around. I want to make this as clear as possible. So, oh dear, why has it done that now? Oh, right. Okay. Okay. Right, so I'll write the ln of x here, and then I'll put the 1 here, right? We can imagine the derivative operator is already acting on this 1, and this is the u, okay? So what would happen if we move the derivative operator over from here onto here, right? So we'll just do this side first. So this is dv by dx, so we need to integrate it to get what v is. So the integral of 1 is just x, okay? And then we move the derivative operator over onto the ln of x. Well, we know the derivative of ln of x is 1 over x. So we get 1 over x times x. And we can already see that these x's are going to cancel. This is going to be a really, really easy integral. Right, now we just need to sub in what u and v are. So if the derivative of v is 1, then v is x. And then u, we already said, was ln of x. Right, and this isn't something we need to integrate. This is just something we have between limits, or in the case where I don't have an a and a b, this is just the function we have. And then this is just the integral of 1, which is just x. So we see that we have ln of x times x minus x, or x times ln x minus 1, okay? So that's a cheeky way of integrating the natural log of x, just by noting the fact that we can move the derivative over as ln of x. The real step is to say ln of x is 1 times ln of x, and then we can imagine this has already been a differentiated function, and we can move the derivative over, okay? That's one way of thinking about integration by parts. Okay, cool. And I think for most problems, again, at A level, they'll tell you solve this by integration of parts. They might not tell you which one to set equal to u and which one to set equal to v, but you only have 2 choices. So if you've got a question, you're struggling, you're like, oh, I don't know which one to do. Well, for this one's quite easy, right? There's only 2 functions here, and you know we can't integrate ln of x really easily. So you probably want to make this the one that you end up differentiating. So this you want to really set equal to your u, and this you want to set equal to your v, which is what they've done here. Right, okay, cool. So yeah, that is integration by parts, really, really important. So you really need to remember that one. Let's see how much of this topic we've got left. Right, this one's a little bit longer, this integration topic, and the next part we do is numerical stuff, and it's really, really fast. So I'm going to take a bit more time on this one because it is so important, as I say. Integrating powers of sine or cosine. Right. So remember, the core of integration is differentiation, right? If we know how to differentiate functions, we're going to have a good time when we try and integrate them. Right, so just have to remember stuff like the derivative of sine is cosine, and the derivative of cosine is minus sine. And then, which means obviously the integrations go the other way. So as long as we remember these 2 things, we can always figure out the integration. So again, the key concept of integration is being like, what differentiates to this? at the end of all your integration answers, a good thing to know, a good thing to do even, is that when you have these problems you're doing in your A-level exams, if you get an answer and you've done a quite hard integration, differentiation is quite a lot easier. So you should probably try differentiating your answer to see if it gets your integral. It's a really good way of checking. Another good way of checking actually is to, if you have those scientific calculators, is to put in the function, even if they haven't given you limits. So say they've just asked you to write down the form of the function, they haven't given you an A and a B. A good way of testing your answer is to just integrate it numerically between two limits, and then also try putting in those limits into the function, the analytical form you have. And if those are the same, try it for a few different values just to be sure. If those are the same, then that's a good idea that your integral might be fine. Again, remember, differentiating is also a good way of checking if it's fast enough. Okay, so yes, integrating powers of sine and cosine. So we know how to integrate sine, we know how to integrate cosine because you know how they differentiate. What's harder is to integrate when we have powers of them. Easy ways to do this are, so one way is just to know things like the trig identities. So knowing cos 2 theta is always a really important one. So cos 2 theta is the same as cos of 2x is the same as cos of x plus x, right? It seems a bit stupid to write it this way, but we know from our trig identity, this is the same as cos of a plus b is the same as cos of a cos of b minus sine of a sine of b. In this case, a and b are the same, so we get cos squared x minus sine squared x. And then we know sine squared is 1 minus cos squared, right? So we get 2 cos squared minus 1, and then we can just rearrange what cos squared is. So here, that's what they've done. And you can do the same thing with sine squared. So instead of saying that sine squared is 1 minus cos squared, you could have said, well, cos squared is 1 minus sine squared. And we would have had 1 minus 2 sine squared. And again, we could have rearranged this to find sine squared as the subject of the formula, and we would have gotten this answer, okay? So the cos 2 theta angle identity is really, really important. You don't really need, or you do, no, you should know it. You should learn it. It's actually really good. So I'll write it down here, just cos A plus B. It's one of the few things I remembered for A-level maths. I don't think in general it's a good idea to just remember loads of things. It's better to be able to work them out. But this saves so much time. So sorry, sine B. Okay, and then if we have a 2x here, we can just imagine x is A and x is B. So then these functions become the same, so they become squares. It's a bit of a cheeky trick, but now that you know, it should be quite easy to remember. Okay, so that's how we can integrate some powers. Right, how do we do that when m and n are, so in this case, m was 2 and n was 2. How do we do that when they're bigger numbers? So it says here that we can factor out powers, maybe. We can use Pythagorean identities. Another way of doing it, actually, I don't think they touch on here. I'm not sure they do. Maybe not. You might not have done it yet. It's interesting in of itself, so it might be worth knowing anyway, is to know if you know Euler's identity. I think it's called Euler's identity. No, it's called De Moivre's theorem, sorry. E to the I n theta, or it could be nx in this case, just a dummy variable. E to the I nx equals cosine of nx plus I sine of nx. Okay, so this is just a result that comes from complex analysis. E to the I nx equals cos nx plus I sine nx, but obviously this is the same as e to the I x to the n, right? That's just power law. And this is the same as e to the I nx when n equals 1, right? So what is this when n equals 1? That is just cos x plus I sine x, right? And we need to raise it to the power n, right? So just to recap, e to the I nx is equivalent to e to the I x to the n. These two must be the same thing because of the way indices work. And then this was equal to cos nx plus I sine x. You just had to take my word for this. If you haven't seen this before, you might see it later, so don't be too worried about that. And this must be just using the same formula, but for n equals 1, raising it to power n. We have cos x plus I sine x, right? And what we could do is we could expand this thing out using the binomial theorem, and we will have if we just compare the real parts, so the real parts must be equal to the imaginary parts, we'd get cos nx equals, and then maybe cos the nx will be one of the terms, and then we wouldn't have a cos n minus 1 term because that would have an I in front of it, but we would have, so I don't know if it's a plus or minus, I'll just put plus here, cos n minus 2x, and then there'll be a sin x term. There should be some number in front of here, which I wouldn't know what it is. I can't bother to write it down. But yeah, that's one way of getting powers of x. Another way is just saying, well, for example, integrating sine cubed is hard, right? How do we integrate sine cubed? I already told you sort of how to integrate sine squared. We can do it like this. Sine cubed, how do we do that? Well, that's the same as, right? Sine cubed is the same as sine squared times sine of x, right? And sine squared is the same as 1 minus cos squared. Okay, this seems like a bit of a stupid thing to say. How is that going to help? We're just making it more complicated. Well, just bear with me for a second. So if I distribute sine x times 1 minus cos squared, I get sine x minus sine x, right, times cos squared x dx. Okay, sine x is easy to integrate. That integrates to minus cosine x, because if we differentiate cosine of x, we get minus sine of x, minus 1 in front, so we get positive sine x. Now, where the real magic comes in is that sine x times cos squared of x, sine x is the minus sine x is the derivative of cosine of x, right? So okay, let's imagine what would happen if we differentiated cos cubed x. Again, this might seem like a bit of a leap, but just bear with me. That is 3 times cos squared of x, just doing the chain rule. So multiply by the power, take one off the power, multiply by the derivative, minus sine of x. Okay, which is exactly the same as what we had, but with a factor of 3. So if we divide by the 3, we can see that's cos cubed x. And again, if we just imagine quickly, plus c, if we imagine quickly just differentiating this thing, the c goes away, minus cosine of x does differentiate to sine of x. We multiply by the power, so that cancels. Cos squared, good. And multiply by the derivative of this thing, which is minus sine of x, great. Okay, so that's just one way that we can integrate powers of x. The same thing, by the way, you can try doing it yourself. Maybe try integrating cos cubed of x. It's essentially exactly the same idea. Just there'll be a little bit of sign messing up because it's different. But yeah, you can try that one for yourselves if you want. Okay, so yeah. Integrating powers. If m and n are both even, then we can replace all the even powers using the double angle identities. So the double angle identities, we talked about those a little bit. So you can try that for yourself. If m or n equals 1, or they're both 1, that's quite an easy case. That's just cos x times sine of x. But basically, all this stuff is when you have powers of cos x and sine x, it's all just messing around with these double angle identities, or doing things like rewriting sine cubed x as sine squared x times sine of x. Okay. Okay, cool. And here they've asked you to prove this identity. How have they tried doing that? Well, you're just using the double angle identities. Okay, so you knew what cos 2 of x was, and cos 4 of x is the same as cos. This is the same as cos of 2 theta plus 2 theta. So you could work through it that way. Yeah, so it's all just using double angle identities in order to get these powers. Okay. Okay, cool. And once you prove that this is the same as the thing you started with, then this is quite easy to integrate. So when you have single powers here, so this is cos theta to the 1, cos theta to the 1, this is quite easy to integrate. Because again, well, let's just recap. How do we integrate cos 4 theta? Well, let's try a sine term, right? Because we know sine differentiates to cos. The argument needs to be the same because this doesn't change. The argument doesn't change when you differentiate something, right? If you differentiate cos theta, it doesn't then suddenly become a cos of theta over 2, right? So we need to have the same argument. And then if we differentiate sine of x, then that would give us cos of 4 theta looking good, but we'd also get this 4 in front. So we have to put a 4 out here. There we go. So that means that the integral of a quarter sine 4 theta equals cos 4 theta. Okay, cool. And is this the end of the section? No, there's more faffing around trig functions. All right, there's one more thing. This is more in the numerics category. Oops. Yeah. Yeah, this is more in the numerics category, but this is the way of integrating things. So I already told you that, well, this is a way of integrating things numerically. So this is how sort of computers will come into play. So I already told you that integration is the same as finding the area under a graph for some function f of x, x-axis. Right, so numerical integration, first thing, trapezium rule, we need to integrate this between bounds, right? Computers can't, well, they might be able to, but in a simplified version, computers don't give us the functional form. They just give us they'll just give us different data points of this thing. So if we're trying to find the area of this f of x function, it's not going to give us, it's not going to integrate sine of x, and it's not going to tell us without the bounds that, oh, this is cosine function, right? The best we can really, I mean, they sort of can do it, but they sort of can do it now, but that's very, very complicated. In a sort of simple numeric sense, the best it can sort of do is, well, if we give it a bound, it's not going to tell us, oh, this is a cosine function, but if it tries to numerically figure out what this looks like, it will be able to plot it, and it will look sort of like a cosine function. Okay, so that's numerical integration, really. And how does it work? Well, we think of things geometrically, okay? So we think of f of x like this, and we imagine, so if we want to integrate this function, we imagine we're trying to find the area of this function. And one way to do that would be to just split this range, say we're integrating from A to B, split this range into lots of equal bins, right? And what I mean by bins is that this gap, I will call it H. This gap is the same as we move along between this range, okay? Right, and now if we wanted to find the area under this graph, so we split everything up into bins, we can then approximate, we say, oh, what's the area under the graph? Well, it's just the sum of all these. We can join the lines on top, so we draw straight lines between these lines. Okay, and so this is a trapezium now. So this has a length f of a. I'll draw it over here, and then this one next to it. So I'll just zoom in on this one. So it's a trapezium. This one has side f of a. This one has side f of a plus h because we moved along h. And the length of this trapezium is h. What is the length of a trapezium? I think it is, don't we just average f of a plus f of a plus f of a plus h over 2 multiplied by h. So that's the area of a trapezium. Just double check if that's right. If f of a, if these two are the same size, then this will be twice f of a divided by 2. So yeah, okay. So this is, I think this is the right formula for the area of trapezium. So we split this area into loads of little trapezia, and we figured out the area of one of them. Now, to figure out what the whole area is, we need to sum all these trapezia, right? The first thing to notice is that, so if we just think about, okay, this is the first trapezium. What's the next one? The next one, well, it has side length f of a plus h, right? Because it's still, they share a common side. So this one, so we just integrated number 1. Let's integrate number 2. One of the sides is f of a plus h. The other one is f of a plus 2h, because we've moved 2 along now. F of a plus 2h. And the area of this one now, so the area of 2 equals f of a plus h plus f of a plus 2h over 2 multiplied by h. And when we do the sum of all of these, right, so we would get an f of a. So each of these terms, first off, each of these terms is going to have an h over 2 factor. So we factor out an h over 2. We see that there's an f of a in the sum, and there's an f of a plus h and another f of a plus h, right? So f of a plus h, this is shared between 2 trapezia. So we need a factor of 2 here. And that happens all the way along. So each of these sides is shared by 2 trapezia until we get to the end one, which is only shared by 1. So we do the sum, blah, 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 blah. And this is f of b minus h. Okay, and that is the trapezium rule. So here they've written it in a slightly different way, but here they see they've got the first height only once, they've got the last height only once, and they have twice times the sum of all the ones in between. And the width of the strip is just b minus a over the number of intervals, and that is our h value. So that's the same thing. Our h is b minus a divided by the number of bins we have, which is called that n. That's our h. And one thing to note about this trick is that if we make n bigger, so the more trapezia we take, the more accurate this gets. But you've got to remember that this function isn't exactly a straight line in between these points, so there will be a slight error. And there's actually better methods of doing this, but trapezium rule is, at this level, is a really good one. There's one more, which is called Simpson's rule, and how that really works, I'll just touch on it briefly, is that we do the same thing, we split everything up into bins. I'm not going to draw the function on because it'll make it more complicated. So in the trapezium rule, we do straight lines between these. In Simpson's rule, we draw a parabola between them. Okay, and this parabola method is much more accurate because functions are slightly curved. Okay, cool. So I think right. Should we stop and then do the next two? Right. Can anyone speak back? Are your microphones on? Hey, yeah. Do you want to? Right. So do you want to take a break now? It's up to you. We can take a break now, and then come back. I want to do, whenever I do this numerical one because it's so small, I want to do it with one more section because it's so tiny. So we can either do it. We can either do it now and then take a break, or we can take a break and then do it with the next one. So it's up to you. It's whichever one you want to do.
I don't really mind. You can choose.
I can choose. Okay. How about this? Is kind of similar. So this numerical stuff is sort of similar to trapezium rule. So I'll just go over it quickly, and we'll take a break around then 2, and then we'll come back. And then, is that all right?
Yeah.
All right. So we'll just do this one more. Right. So solving equations numerically. I should get through this really quickly because it's really, really tiny. Right. So yeah, we just did the trapezium rule, which is one way of integrating things numerically. Right. So if we want to actually solve equations numerically, well, what do we mean by that? What we mean is that, say we have some function x cubed minus 2x plus 6 equals 0. Right. We want to find the. I hope this isn't an easy one. I don't think this is an easy one. Let's imagine it's kind of hard to find the roots of this. I think it is. So what we want to find the value of a such that f of a equals 0, right? So we want to find the root. We want to find where this curve, so it's minus, and then, so it looks maybe a bit like this, and then it might look like that, it might not. Oh, plus 6. Let's imagine that's 6. Whoops. And then this is 0. It might look something like that. I don't really know. We want to find the value of this where it crosses the x-axis, which I've drawn here, and then this is the line y equals 6. Because I messed it up a bit. So yeah, when we're finding roots, we want to talk about finding the value where this crosses the x-axis. Okay. What's one way of doing this? So one way of doing this would be to just guess, really. So all right, we'll try maybe 1. So the value of 1, that gives us 5. All right, that's not really good. And then looking at this graph, well, if we've sketched it sort of right, then we'll see that the more negative value we get, the sort of closer it is to, the more likely it is to be 0. So let's try -2. That would give us a -8, plus 4, plus 6. All right, that gives us 2, right? Okay, so that's closer. Maybe if we try -3 is going to give us -27. Plus 6 equals 12. So is that -15? Maybe, I'm not sure. Tell me if I make a mistake. But the essential idea is that we guess values, and then we know something called the intermediate value theorem. Okay, and what that means is that, so when this was for x equals -2, this is for x equals -3, and we saw that when we put an x equals -2, it was too big, so we're sort of on this side. And when we put an x equals -3, it was too negative, because remember, we want to get the answer 0. So by the intermediate value theorem, we know that there must be a value in between -2 and -3 such that when you put it in this function, it will give you 0. So that's what the intermediate value theorem is. I don't know if it says it here. I don't think it doesn't. But yeah, there's no way, if you have a function and at one point it's above the x-axis and at one point it's below, there's no way you can connect these lines without it passing through the x-axis at some point, right? Unless it does something sort of illegal like this, but that wouldn't be a function then. Okay, the way it's drawn, that doesn't make any sense. So there must be in this range a value, i.e. here, such that when we put it in, it gives us 0, okay? And that's the intermediate value theorem. So now what we might try is we might try a value in between -2 and -3. We might try a value of -2.5. Let's imagine 2.5 didn't work, it was positive, but then -2.6 did work. We then know it's in between these. So we might try -2.55, and we keep going. And this is called a decimal search. And then, unless you have, you've drawn a graph and you get a pretty good guess straight away, it's not a very good method. It's a bit rubbish. But I think the sort of best way of algorithmically doing it is to choose a really big value, then choose one that's really small, and then halve it, and then keep halving it every time. So what we did here is we chose a value that was a bit too big, a bit too small. We halved it. We tried that. We saw whether it was too big, too small. That makes us decide whether to go up or down, and yada yada yada. In general, it's a terrible way, but that would be how you do it. And they might ask you to do something like that in the exam. But you're using the intermediate value theorem. So that's the sort of thing to remember. Okay, another way of doing it is iteration, right? So we started with this equation, and then potentially, for some equations it doesn't work, but potentially there could be an iterative formula such that the n+1 solution equals, and I'll tell you what I mean by this now, equals 2x minus, oh goodness gracious. Right, let me just sort this out. Equals 2x minus 6 to the power of a third. And this is n. And what this iterative formula is saying that if you have some value x of n, to get the next value, the next best approximation, you put that value in this formula, you double it, you take away 6, and you take the third power, and that gives you the next one. And then to get the n+2 one, you then put 2x n+1 minus 6 to the power of a third. Okay, and in your exams, they're not going to ask you to figure out these formula. They're just going to ask you to use them, which is quite simple, or at least that's what they did for my exams. I'm pretty sure that's what's going to happen. What you can see is that you don't need to know this, but what they've sort of done here is they've really badly arranged this equation. They've tried to make x a subject, but what they've done is they've accidentally left x on the other side. But it turns out that this process sometimes converges. It converges for specific functions. You don't need to know when it converges, but that gives you a sort of inkling of where the theory behind it comes. I think this might be a fairly complicated subject. I'm not exactly sure, but yeah. So in practical terms, in just the sense of using this is you have an initial guess. The initial guess can't be too ridiculous, otherwise this won't converge, right? If we try, can I think of any value? I can't think of any values for when this wouldn't converge. If we imagine that this wasn't a 3, if we imagine this was a 2, if it was x squared minus 2x, minus 2x plus 6. I know you would never try and solve this method using this iterative way because it's really easy to just complete the square, but then that would give us the exact same thing as we had before, but instead we'd have this half here. Well, actually, no. Let's imagine this is a 4. Right, that makes it even better. Right. So now, if we try a guess that's too small, so if we try a guess of 0, let's try a guess of 0. It's a really stupid guess. And then we'd be trying to take the 4th root of a negative number, which wouldn't work. Okay. So just to iterate, you can't just choose. Just to reiterate, you can't just choose some random value. They'll often give you a value, or they'll give you a range of values to choose from. And then when you put that number in, the process will converge. And you'll see that as you try and find the n+1 value, it will get closer and closer and closer to some value. And you can use that value. Okay, so that's what iteration is. And is that? I think that's basically the topic. There's one more thing that isn't on here that I want to talk about, and that's something called Newton-Raphson numerical methods, or I can't remember what it's called, Newton-Raphson something. And it's a method for finding zeros. And essentially how it works. I guess you don't need to know this, but you might. But it's just one more way of doing it, just for completeness, is that, oh, sorry, this doesn't intercept the x-axis, does it? Whoopsies. It needs to be a function, obviously, that intercepts the x-axis at some point. Otherwise, you're just going to get a weird answer. Oh, has this line disappeared for you? It keeps. Is it? Am I deleting that? Because it keeps happening to me, and I don't think I'm doing it, but I must be. I don't know what I'm doing. Right, just please tell me if it happens again, because sometimes I don't know this. Right, okay, so this is f of x. A good way of maybe finding the roots of this, okay, we could guess, as I said before, we could do this iteration method. One way of maybe trying it would be to, okay, let's guess this value. And what we could do would be to find the derivative at this point. So say this is our guess, is our a. I'll denote the derivative by f dash of x. We could find the tangent at this point. This is the tangent, which has a gradient m equal to f dash of a. And we could go along this line, find out where this intercepts the x-axis, and then try finding the derivative here, which is, we'll call this new point B. And then this line has a gradient f dash of B. Right, yeah. And then we could then find where this line intercepts the x-axis. So again, to do that, we'd be using things like y equals mx plus c, or y minus this coordinate geometry stuff. Y minus y1 equals m of x minus x1. Right, so we can use this. We know the gradients of the curves. We know a point. We know a point that it's at, and we can put it into the formula, and then we can then find the x-intercept of this line to get. So that's how we'd get this point. And then we then do the same process again to get a new point. And then, I don't know if you can see, but this is sort of converging. So it gets steeper here, blah, 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 blah. So this would be the new point. And then we'd go to the graph, and then we'd look along the gradient, blah, blah, blah. And you can see this just keeps converging until we eventually end up at the point. Okay, and that's called Newton-Raphson. So just to summarize what that was, is we choose a point, we find the derivative, we construct a line out of that derivative, and then that gives us a new intercept. And because of the way the gradient points, the gradient sort of points us back towards this origin very roughly. Then when we do that again, it's going to make us converge in at this point. So that's called Newton-Raphson integration. Okay, or I can't remember what it's called, Newton-Raphson something. Right, okay, so we've done quite a lot there. Do you guys want to take a quick break or something, toilet break, I don't know, whatever. And we can start back at 2, sorry, right?
Yeah.
Okay, cool, right, I'll give you 5 minutes.
Hello?
Hello? Hey, I didn't know how long you'd be, so I just sort of waited here. Is everyone back? Hello? Oh, please tell me my microphone's working.
Hello? We
Hey,
hear
can you hear me?
Yeah, we're back.
Do I cut out sometimes when I'm speaking?
No, you're fine.
Oh, that's good. Right, okay, that's good. Right, yeah, so everyone's back, yeah?
Yeah.
Okay, cool. Right, we'll get on to vectors then. Maybe I should make a new page because I learned how to do this just now. Add page. That's probably fine, isn't it? And then I need to close this. Okay, cool. Right, yeah, I made a new page because I think it's big because there's quite a lot of stuff to talk about and drawing to go on with this topic because it's vectors. Yeah, right, cool. So let me just close this bit off. Right, vectors. What is vector? I think we've talked about vectors a little bit. Sorry, there's a tractor going past. Can you hear that, or is it not that bad?
We can't hear it. It's fine.
Great. Okay, good, because it's really loud. Okay, vector. What is a vector? There's sort of two ways of thinking about vectors, I think. One of them is a directed line segment. This is the mathsy way of thinking about it. So that just means that it's a line in space in 3D or 2D or 1D or more if you want to be pedantic. And it's a line and it has a direction along. Okay, so it's not just good enough to say I am r away from the origin here. I have to say I'm r away and it's in this direction. I don't know why I draw the other arrow on. This other arrow is not what I want. I just want this one. So I'm this far away in this direction. Okay. Another way of thinking about it is sort of in a more physicsy sense. A vector is you can think of it as like a physical arrow in space. So again, it's got a distance, it's got length associated with it. So it could be like a massive ruler in space along in one direction. The pretty similar way of thinking about it. This is more mathsy, so this line segment thing. But you can just think of them as just arrows in space that just sort of point in directions. Okay, they're essentially exactly the same thing. Right. So how do you write vectors? We'll think about Cartesian axes. So this is your x-axis, this is your y-axis, this is your z-axis. Let's imagine putting unit vectors. Let's imagine this concept of unit vectors, or unit vectors. And as their name suggests, these vectors are the building blocks of all bigger vectors. Okay, they're called unit because they have length 1, and they point along the axes. So here's one, and it's called I. The one that points along the x direction is called I, or you can call it EX with a little hat. The hat means it's a unit vector. Okay, so the hat means it has length 1. This one's called J, or you can call it EY. And then this one is called K, or you can call it EZ. Okay, so what unit vectors are? They're vectors of length 1 that point along the x, y, and z directions. And it turns out that now that you have 3 vectors that are orthogonal to each other, they don't need to be orthogonal to each other, but what this means is we can now write any line segment in 3D in terms of these unit vectors. So let's say we wanted to get to the point over here. So what this construction means is that I'm this far up, call it C, and I am at some angle along in the XY direction. Okay, so if I want to get to this point, obviously I need C lots of K. If I want to write this vector, I need C lots of K because I need to go up by an amount C. Let's say I am Y along the Y along the Y direction. Sorry, I'm B along the Y direction, and I'm A away from the y-axis and A along in the x direction, then that means I just need to add BJ and then AI. I've forgotten hats. Okay, so just to recap, if this has coordinates if this point has coordinates A, B, C, then to do the origin vector, the vector that points from the origin to that point, I just multiply each one of these by I. I can also write this in a different form, so I can write it as something called a column vector, like this, and this just means exactly the same thing. It's just a convenient way of writing things. I don't have to worry about all these silly unit vectors. Okay, and yeah, so that's what this is written here. So this is some vector r equals 1, 3, minus 2 plus t times 1, 1, 3. So this t is just a parameter which moves you along the line. And if I just expand this out in terms of the unit vectors, so I need 1 times I, 3 times j, minus 2 times k, which is what they've got here, and then t times 1 lots of I, t times 1 lots of j, t times 3 lots of k. So that's what this part is here. Okay, and we can now talk about something called parametric form. So we can write all these vector equations in terms of different parameters. So we could choose to write it in terms of t, or we could choose to write it in terms of x, y, and z. And if we do that, then we can get different forms of the equation. So really, even though this looks really, really complicated, this expression, it really is the same form as this. And we can see how we've gone from this to that is we've taken our x value, our y value, our z value. We took away what the coefficients here. So we had x minus 1 because there's a 1 here, y minus 3, and then z plus 2 because minus 2 is plus 2. And then we've divided by the coefficients in front of the t. Okay. So that's another way of writing exactly the same line. So that's how you go from this step to this step. Okay, so that's equations of lines. Oh, I didn't need. Do you know, I don't actually think I need this. Can I get rid of it now? I thought there'd be a lot more drawing. If I delete, it's not going to delete everything, right?
Hopefully.
Yeah, let's hope this doesn't. Yeah, that's fine. Okay, good. That's close. Probably shouldn't have done that on stream. Whatever. Okay. Okay. Should we talk about? No, we don't need to talk about dot products yet. Where does that come? Okay, we'll talk about dot products later. Parallel line, skew, or intersects. Okay, so if we have this line is OA, A plus SC. S is just some parameter, I think, like we talked about before. They tend to use the symbols T and S for parameters because of the alphabet or whatever. Right, so OA, let me just draw that on. So every time you see an OA, this O is the origin. And the A is the point. And the way this arrow is drawn means you're going from O to A. So this is called a position vector. It's always really useful to write, or almost always really useful to write all points in terms of their position vectors. And this position vector takes you from OA to some point, which is A away like this. So this A is like, you know how we have y equals mx plus c, right? This A is like the C term. So this takes you onto the line. And when s equals 0, that is the intercept. And then this s value multiplies by c, which is another vector, and c takes you along this line, okay? So just to recap, the equation for this line was A gets you onto the line, and then when you start multiplying by s values, that moves you c along the line. So c is a vector that points this way. A is a vector that takes you onto the line, and when then you multiply c by some value of s, that allows you to move along the line. And the same thing is true for OB. It's a position vector for a point on a line. Okay. For lines, if these lines are parallel, right? So this was the intercept. For them to be parallel, the gradients need to be the same. Okay, and the gradient is s times c. So for the gradient, the gradient is the vector c. Okay, because remember, you move c units along this line. So A takes you onto the line, and then you multiply c by some number to move along the line. So c is like your gradient. And if lines are parallel, to have their gradient the same, so if we think about, let's think about the 2D case first. So if two lines are parallel, then their gradients are the same, right? So these two lines are parallel. If this line isn't parallel to these two lines because they eventually intersect because their gradients aren't the same, when we then generalize to 3D, in order for these lines to be parallel, C and D must be equal or be some ratio of each other. If they're not equal, if they point in slightly different directions, then the lines aren't parallel to each other. Okay, cool. And I think we can figure out we will know how to figure out whether lines are parallel. We'll figure that later when we start talking about the angle between two lines. Okay, so intersects. How do we find if two lines intersect? Well, we suppose that these two things equal each other, right? This is how we do most equations in maths. So what this means, setting these two equal to each other, means that there is some point for some values of these a, s, b, and t. This point is on both lines. So when we put in this point's values, it must satisfy both equations, and then we can just solve these equations. This is really, so if we just think about the x components, that will be one set of equations. So we have the x value of the a plus the s times the x value of the c, and that will equal the x value of these. And then we'll have the same one for y, and we'll have, well, not the same one, we'll have a different equation for y and a different equation for z. So we get three simultaneous equations, and we can solve those to figure out what point satisfies both of these, okay? So that's one way of doing it. Okay. It can be easier. Sorry, to change this, to sort of make this process quicker, it's probably a good idea to check first whether the lines are parallel or not. You don't have to do this, but if you do this, because you might end up with a set of simultaneous equations that can't be solved, and if they can't be solved, that means that the lines are parallel. So you probably want to check if they're parallel first. As I said again, you don't have to do it, but it will make things a lot easier. Then you set them equal to each other. Then you carry out the simultaneous equations. And then if you can't get a solution, that means the lines are skewed. That means they don't intersect. So even though they're not parallel, they never intersect each other, which can happen in 2D. So if you imagine two lines, they're not pointing in the same direction, but if this one sort of passes under this line, then they're still never going to intersect each other at any point, even though they're not parallel. Okay, cool. So this is kind of hard. This stuff's kind of hard because it's all thinking sort of geometrically, but you can make it a lot easier by thinking in terms of components. When you think about just components, then you start to see that even though this looks quite complicated, it really just is three simultaneous equations. And then remembering what parallel means. So when we go from 2D to 3D, remembering that parallel means that these vectors are either the same or they're multiples of each other. That is a key step to being able to figure out if lines intersect or not, okay? Okay, so this stuff is less sort of visual. This is the angle between two lines, okay? So how do we figure out the angle between two lines? Well, we have this formula already for us, and if you just accept this formula, it turns out that basically all the vectors becomes really, really simple. So you don't worry so much as to where it comes from. It's sort of just a definition, and what it says is, I'll rewrite it here. So A dot B, so these are two vectors, A dot B. If you divide by the size of them, so this is what this modulus sign means. In one dimension, modulus just means make something positive. So I've drawn two dimensions here, but let's just imagine we just have this one dimension here, this one axis. If you take the modulus sign of x, that just makes sure it's always positive. So if we had 2, 2 stays as 2. If we had -1, then we want to take the size of it, so it moves over here. In sort of 2D, the way to generalize that would be how long is this line? So modulus is the same thing as saying how sort of large is a number. So if I take the modulus of -3 equals 3, that's telling me that the number -3 is sort of 3 large, just forgetting about the sign. In the same way, when I start taking the modulus of a vector xi plus yj, how long is this line? Well, I can use Pythagoras' rule. So it's x in this way, and it's y this way. So its size is the square root of x squared plus y squared, which is the length, and that's how you figure out the modulus of vectors, okay? So that's just how you figure out these moduli. And what we say is that when we do the dot product between two vectors, so I haven't told you what this is yet, that equals the cosine of the angle between them, okay? Right, so how does this work? Let's try and figure out what the dot product is between I and itself. So we want to think about this geometrically. So we'll draw our axes. We have some I along in this direction, some J along in this direction, some K along in this direction, right? So what is the dot product between I and I? Right, the size of I already told you I is a unit vector. So the modulus of I is just 1, and the modulus of the other I is obviously still 1. So we have a 1 on the bottom, and we have cosine of the angle between them. What is the angle between I and itself? It has an angle of 0, right? Because there's no angular difference between I and itself because it's the same vector. So cosine of 0 is 1. So we see that I dot I equals 1. And we can make the same argument for j and the same argument for k, because the angle between k and itself is still 0, the size of it's still 0. So we actually see that this is true for j and k. They're all just equal. The dot product with them and themselves, they're all just equal to 1. What happens if we try and take the dot product between I and j? Well, the size of them again is still 1, so I won't bother writing that in. But now, because we know where I and j sit, we know the angle between them is 90 degrees. But cosine of 90 degrees is 0. So we see that the dot product between I and j is just 0. Right, so now that we know how to take the dot products between those two things, how do we take dot products of, let's say, ai plus b times j? How do we take the dot product of this times maybe ci plus d times j? How do we take the dot product of this? Well, the first thing to know is you couldn't really figure this out, but if I just tell you that this behaves just like a normal number, so it's a lots of I, when we multiply this through, we will get an a times an I dot with a c times an I plus an a times an I dot a d with a j dot with b j c I. So I'm just multiplying out this whole bracket, and then b d j dot with j. So the dot product between I and j was just 0. So again, these are just numbers, so these can just be moved through here. And the dot product between I and j was 0. So this one equals 0. This one also equals 0. But the dot product between I and itself is 1. So this whole thing just equals AC plus BD. And if we just look back to where we started with, we see that all we did was multiply the coefficients together when they had the same index. When they were multiplied by the same unit vector. So we had A times C plus B times D, and that's how you take a dot product. So in general, if you have an X, a Y, and a Z, so this is a vector. I've just written it in the, I've written it in the vector notation, just because it's faster. X, oh my gosh, done it again. X, Y, Z, dotted with ABC, all right. Then that just equals AX plus YB plus CZ. Okay, so you just multiply the same coefficients together and sum them. Okay, so that's how we do a dot product. And now that we know that, now that we know how to do a dot product, we can figure out the angle between any two vectors really easily by just saying theta is the inverse cosine of the dot product divided by the moduli, which is the size of the vector, the length of the vector, which we get from Pythagoras' theorem. Okay. Right, I might make a new, I'm going to make a new thing, and I'll actually use it this time, hopefully. So, add page. Cool, right, so finding the equation of a line. Right, so let's think about position vectors again. I've said they're useful, but I didn't really explain or show you how they're useful. So let's say we have some point A over here, and we have some point B over here. I'll just draw on some dotted lines so you can see sort of where I'm imagining they are in space. So A is here, and B is much closer to the ground. I wish there was a faster way of drawing dotted lines. It probably is. I'll try and figure it out some other day. Okay, so the position vector is the line that takes you from the origin to the point, and it's denoted by OA, with this line telling you going from O to A. And likewise, the one for B is written like this. If we want to figure out what is AB, so AB is the position vector going from A to B, how would we figure that out? Well, we know that if we start at A and we want it to get to B, one way of doing that would be to go back towards the origin, the AB, starting at A, going to B. We could start at A, we could go backwards from A. So OA points in this direction. If we want to go against OA, we need a minus sign here. And then when we get to the origin, we can then go from the origin to B by going along OB. So that's why position vectors are so important. If we want to figure out the line that takes us from A to B, that's the same as minus the position vector of A plus the position vector of V. Because we start at A, we go back to the origin, then we go out to B. Okay, so we can find, if we know, if we want to find the equation of a line, what we could do is to say we know 2 points. So anytime we have 2 points, that completely defines a line because there's only one way to draw a line through them. One way to find the equation of the line, first you find the gradient, and the gradient, AB, so these are the 2 points. The gradient is the line that points, is the unit vector that points along this line. So we can find that using this thing. So we just take the position vectors and find out what this line vector is. We can make it a unit vector. So AB, this little hat means it's a unit vector. We can make it a unit vector by dividing by the size of itself. So if this had a length 3 and we divide by the size of itself, which has 3, we'll still get a vector that points in the same direction but only has length 1. Okay, so now that we've got the directed line segment, all we need to do is figure out how to get ourselves onto the line. So we could use either of these vectors. We could use maybe the position vector of OA. So our equation of the line would be OA. That gets us onto the line. And then to move along that line, we need some number that takes us along the line, multiplied by our little unit vector thing that we just figured that out. Okay. So yeah, that could be one way you do it. Or equivalently, you could do it like this. OB, you could go onto the line by going onto B, and then you could move T along the line AB. Okay, so that's how you figure out position vectors. So you take 2 points, you figure out the vector that takes you between them, you normalize it. You don't have to do this, but when you do normalize it, that means that S is now an exact distance along the line. Because if this has length 1, then say S equals 3, then you're 3 lots of 1 along the line. So S corresponds completely to a distance. If your vector AB was like 10 long, then when S equals 2, you're actually 20 along the line. So it makes it a little bit annoying. So that's why this step, although it isn't essential, is often done because it makes everything simpler. So yeah, just to recap, you take your 2 points, you find the vector that goes between them, you normalize it. You don't have to do, but often helps. And then you just say that when you want to talk about a point on the line, first you have to get on the line, and then you move along it. Okay, so that's how you can find the equation of lines. Right, distance from a line to a point. Okay, this is another topic which is you have to think about sort of visually. It's a bit annoying, but once you get your head around it, it's not too bad. Shortest distance from the point to the line. So you want to find the vector for point B on the line. So it could, okay, so this is your equation of the line. So this is the vector that gets you on. So this is like your OB or your OA. And then this is the vector. This isn't a unit vector. They haven't used a unit vector here, so I'll keep the hats here. I can tell it isn't a unit vector because 1 squared plus 1 squared plus 3 squared isn't 1. Obviously, so it's not a unit vector. You need, if you wanted to make this unit vector though, well, this is 9, so this is I think this is 11, right? If you divided this, so sorry, that's the size of the vector. When I take the square root, that's how long it is. Pythagoras' theorem, so 1 squared plus 1 squared plus 3 squared. So the length of this vector is square root of 11. If I just divided by square root of 11, that would make this unit vector, just so you know how to do that. Yeah, so you find the vector for the point B on the line. So in this case, if this is OB, then t equals 0 would give you the vector of the point on the line. But maybe this vector is OA, so maybe this vector takes you to point A. Well, you'd need some different non-zero t value to give you the point OB. And Yeah, so here, okay, so here, what they've said is, so you have your equation. Let me rewrite this. Your equation equals something that gets you on the line. This is like your OA. And then something that moves you along the line, which is your T times 113. If you want to find OB, then OB must satisfy this equation. So OB is something like 3 plus T minus 2 plus 3. So for some value of T, this will give you the vector OB, which is what I think they've done here. Yeah. So if A is this, then wait, are these two different lines they're talking about? Oh, so let me reread the question. I might have been understanding this differently. Distance from a line to a point. Yeah, okay. So this must mean the distance from a point on the line to a point. Sorry, the way they've done this now is the point B is no longer on the line. Oh wait, find the vector point. So sorry, B is on the line. A isn't on the line. Right. Oh, sorry, I know what they mean. So this problem, right? Sorry, I thought it was something else. This problem is trying to find if you've got some line like this, going this way in space. If you've got some random point, what's the shortest distance between the line and this point from the point on the line? I think so. I'm not really sure. It's not really set up different. Does anyone know what he's trying to? Does anyone know what he's trying to say here? I'm not really sure what the question is I'm trying to answer. Distance from a line to a point. Is this any line to any point, or is he trying to find the smallest distance between a line?
Go down. Are there like? Is there like?
I don't really know. He's just finding points. Use Pythagoras theorem. Maybe I should come back to this. I don't want to get too bogged down on this one thing. Because I think he wants to find the point on this line that's closest to some other point that's not on the line. So if you have, well, I might just answer that question anyway. So say you have some point, I don't know what to call it because I think he's got a different name. Oh goodness. So say this is some point A, and you want to find what is the point on this line that's the closest to A. I think that could be a good question to answer. So say A is, I think that might be what he's doing. Yeah, okay, so say A is this point 2, 3, 4, right? I hope this is the question he's trying to answer. If he's not, then this is still a useful thing to know anyway. So you want to find a point on this line that's closest to A. And it turns out that this is going to happen when the line between A and B is perpendicular to the line, isn't it? That's when it's close. If this angle isn't quite 90 degrees, then you could always make it smaller by moving it back in. Okay, so this is the point A equals this. And then B is the position vector of B, because remember, B is on the line, so it satisfies this equation. We don't know where B is yet. That's what we're trying to find out. We want to find the value of B that works for this, okay? So this is our B. It satisfies the equation, so we've just written it in this form, and this is our A. And we want to find what value of T makes this point closest to this other point. Okay, so what we could do now is find what's the distance, the vector between these. What's A to B? Well, that's the same as A to B or B to A. Doesn't matter which one we do. Let's do A to B. It's the same as OA minus OA, because we need to go back towards the origin, and then we need to go out towards B. Plus, oh, dear me. Okay, so how do we do that? We just T minus 1, and then T plus, so I'll put in the full working. So I'm just doing this term minus these ones, okay? So we had T plus 1 minus 2, T plus 3 minus 3, and then minus 2 plus 3T minus 4. So that gives us T minus 1, 0. I was going to put in the minus 3, but I'm not going to bother now. And then 3T minus 6. Okay, so this is the line. This is the line that takes us from A to B. And now we want to make sure that this line is perpendicular to the original line we started with. Okay, so we want to take the dot product. I think that's what he's doing here. Yeah. Okay, now we want to take the dot product between the line that takes us along this one. And what was that? That was just this thing. That was just this 1, 1, 3 thing. So we do AB dotted with, what did he call it? There's no name for it. We'll just call it 1, 1, 3 then. Okay, so we get T minus 1, T, sorry. When you do the dot product, you always get a number. So this should be T minus 1 plus T plus 3, 3T minus 6. And if we just solve this equation, I think this is the question he was trying to do. We get T equals 19 over 11, but this isn't the final answer, okay? This is our value of our parameter. We need to put this into the equation, and that gives us the actual point that's closest to the line. Okay, so just to recap, we had one line. First we had a point. We had some line. Oh dear me! Can you see that line? Is that on your screens?
Yeah.
This other one. Ah, right. So okay, I thought it was just happening on my computer. Right. So we have some point OA, and we want to find what point on this line is closest to OA. So we have our equation, gets onto the line, T, and I'll call this C. Doesn't need to be a unit vector, but let's say it's here. Okay, so the first thing we do is we figure out what is the line that takes us from A to the point. So what's this one? Once we have that, we make sure that this line is perpendicular to C. So we choose that AB dot C equals 0. And if we do that, that gives us the point on the line. So we're just using the fact that this line has to be perpendicular to the direction line. Okay, cool. I'm glad we finally sussed that out. And then this is what, okay, so that was, is this, okay, then, so what's this stuff? Yeah, so this is, okay, yeah, this is just an example showing that things don't intersect. So it's to do with parallel lines and stuff like that, I reckon. And then I think they'll get harder as you go along. Position vector, blah, blah, blah. Okay, yeah, so there's some good examples to work through there. This stuff is sort of kind of harder if you try and think about it. If you don't know to think about geometrically, it's kind of hard to remember all the steps. But if you just try and remember this way of drawing everything out and thinking, oh, this line has to be parallel to the direction line, then essentially has to be perpendicular to the gradient, then that sort of makes more sense. Right, there's one more thing to talk about, I think, in this topic. One more thing or two more things? Oh, there's quite a lot more things. This is a really, really big topic. I probably should have gone a bit faster. My gosh. This topic's absolutely massive. Oh, we might not even get onto complex numbers. Right, okay. Where were we? There's so many examples. That may be right. All right, equation of a plane. So how do we define a plane? One way of doing it would be to say, so if R is a point on the plane, then if we do the dot product of that with some vector, so okay, first let's think about what a dot product really means. So one way of thinking about dot product is if we just rearrange that formula I showed you before, you see that A dot B is cos theta A times modulus of A times modulus of B. One way of thinking about this is that you can think about it as a projection. So what do I mean by projection? If I say this is some vector B, and this is some vector A, and this is the angle between them, theta, the modulus of A is this size, right? That's the modulus of A, it's the length of this vector, and the cosine of that is the same as this length. This is A cosine of theta. So we see that A dot B is sort of saying, what is the product of A along B? Right? Because it's saying, well, A dot B, I take the shadow of A on B. So imagine if I shine a light from above this, the shadow of A, and I multiply that, the projection of A that is in the same direction as B, and multiply that by B. And then that means that if A was a unit vector, so sorry, if b was a unit vector, then that would be the modulus of a cosine of theta. The modulus of the unit vector is 1. So it's sort of like saying a dot I is the length of a along the direction of I. Okay, so now that we sort of have a different understanding of this dot product rule, we can use it to define planes. So we could say that for some position vector on this line, when we take the dot product, i.e. when we take the projection of this vector along this direction, if that is a constant value, then that means that this, so let's say that this is the vector here, -4, -5, -1 is this one. If this value is constant, then that means that any one of these vectors has the same length in this direction, which means that it defines a complete plane, because the distance from the origin along this vector is the same for all of these points, so that it defines a complete plane. Okay, so that's one way of thinking about it. You don't really need to know that. You could just remember that this equals a constant value. But yeah, that could be one way that you think about it. So the dot product is like the projection. So the projection of all the vectors on this plane is the same, i.e. their length in this direction is the same. The length in the direction I've drawn on here is the same. And then we can multiply this thing out. So if we just say R is some point x, y, z, y, z, then when we multiply out by this, we would just get this equation, okay? So that's putting this planar form into Cartesian form. All right, that was quite fast. Oh no, that can't be the whole topic. Right, cross products. What is a cross product? So a cross product, so we had a dot b equals cos theta times the modulus of a times the modulus of b. Cross product is a different thing. So a dot product gives us a scalar value. A cross product gives us some vector, a different vector. So it doesn't give us just a number. It gives us an arrow in space. And geometrically, so if A points this way and B points this way, the vector points upwards. So if I do A cross B, that equals the modulus of A times the modulus of B times sine of the angle between them. So it's not cosine anymore, it's sine times the angle between them, and then some unit vector that points this way. So I'll call that C. So this vector is at 90 degrees to both the other ones. And what that means is that if I talk about vectors, that means that if I take the cross product between A and B, so if I have two vectors, they always define a plane. So these two vectors we can think of as being in the same plane. When I have three, that they don't necessarily have to be in the same plane, but if I have two, then they're always in the same plane. And what we can think about is that if we do the cross product to them, that defines a vector C that's normal to this plane, so it has a 90-degree angle to this plane, and so this vector C sort of defines the plane. Any other vectors that are perpendicular to the C vector will also be in the same plane. So that's why it's sort of useful in this context. And how we actually figure it out is, well, here's one way of writing it out. LMN, so we take the L times the R value, and we take away the N times the Q value. This is sort of something you just have to remember. If you've done determinants, or when you do determinants and matrix stuff, I prefer to think of the cross product as the determinant of this matrix. So if I do A cross B, then I can write all the components in this matrix, Bx, By, Bz, and taking the determinant of this matrix gives me what the vector would be. So how do I do the determinant of this? A cross B, again, these are just silly rules you'd have to remember. So again, this is a silly rule you would just remember. Or you can just remember this silly rule. This one's kind of geometric, which I like it more. It's a bit nicer. So if I just do the I component, how do I figure out the determinant of this matrix? I multiply these two together, and I take away what these two multiply together. So AX times BZ, and then I take away BX times AZ. And then for the next one, there's a minus sign in front. Don't ask me why, there just is. And then I ignore this. Oh, sorry, I did the first one wrong. Sorry, so if you want to figure out the I component, you ignore anything in the same column as I. Let me just delete these arrows. There's no easy way of remembering this this formula, by the way. It's just a bit of a nightmare. So right, if you want to figure out the I component, you ignore this row. You take the product of these two. So this was AY. God, that's annoying. Let me just get rid of this. Oh, did you see that? Drew this line across on the screen. I just went to erase and it just randomly draws it. It's really, really annoying. Right, okay, it's gone now. Right, so if we want to figure out the I component of this, we ignore anything in the same column as I, and then we take the product of, I should have just deleted everything in one go. I don't know why I kept changing between the razor and stuff. And yeah, we take the product between these two, AY, BZ, and then we then take away the product between the other two. So minus AZ, BY. Okay, then we put a minus sign in front of the J one. So we start by saying, we write down our I, a J, a K, we do plus, minus, plus. That's just the rule. Then we ignore anything in the same column as I, and then we do that thing when we take the product of these two ones, the upper left and the lower right. We take away the upper right and the lower left. And then we do the same thing. So in front of the minus J, we ignore anything in the same column as J. So now maybe I'll change this to purple. So we're doing the J one. We ignore anything in this column, and we do upper left times lower right. So AX, BZ, and then we take away AZ minus BX because that's the upper right, lower left. Okay, and then I'll do one more one. So when we're doing this one, the K one, I should use these colors more often, actually, it's quite useful. We ignore anything in this column and we just do upper right times lower left. This is a bit messy, but I hope the meaning still sort of makes sense. You could just remember this thing, to be honest, as well. This is sort of the same thing. So, okay, we're figuring out the I component. We take M times R, and then we take away N times Q. Okay? And then when we're figuring out the M component, there's a minus sign, and it's N times P. So, is there a better way to draw this? So for the L1, you're doing this, MRNQ, and then for the M1, LPNN, you're doing this. So I don't know, maybe you can remember this, maybe they'll give it to you in the exam. There's lots of ways of thinking about it. So you can either think about it as taking the determinant of a matrix. This will probably make more sense to you when you start doing matrix stuff, or you can just remember this formula. You're just taking diagonal products and stuff like that. I don't want to get too bogged down in this actually, because it's just memory. Right, so the main point is that if you have two vectors, they're in the same plane. When you take the cross product, that defines a vector normal to the plane, and then this normal vector can be used to specify the plane because it's normal to all the vectors that are inside the plane. And by normal, I mean at 90 degrees, okay? Right, so if we have 3 points on the plane, so 3 points always, two vectors defines a plane, or 3 points always defines a plane, right? Because if I draw 3 points, if I draw 2 points, that always defines a line that I draw between them. 3 points always defines a triangle. It also always defines a plane, right? These all 3 points are in the same plane. If I have 4 points, then this one doesn't necessarily have to be in the same plane, so I need at least 3. If we wanted to define a plane from these points, we could make two vectors. So we could make AB and BC. So this is A, this is B, and this is C. We can make AB, which goes between these two. We already know how to do that. We can make AC, which goes this way. And then if we take the cross product, we get a vector that's normal to the plane, and that defines the plane. That's what they've done here. Oh, this normal vector, by the way, is the one that appeared up here. So this is the normal vector. So this is a vector in the plane. Sorry, not in the plane, normal to the plane. -4, -5, -1. This is the vector that all the position vectors have the same component in this direction. That's what it means to be in a plane. Okay, so that's how it gets in the equation. And then this is all stuff that if you've got a line going through a plane, well, I don't know. This is just messing about with lines and stuff. In line of the plane, find one point on the line. What is the objective here? Given a point and a line on the plane, make 2 points on the line, substitute different values of s. What's this? What does anyone know? Oh, finding the equation of a plane. Well, I thought we already did that. That's this. What is this? Does anyone know what this bit is? Given a point on the line. I don't really know what they're doing here. We already know how to get equations of lines if we have 2 points. We already know how to get equation of planes now, because I told you that when you find the normal, the position vector of anything dotted with this normal has to be some constant. Yeah, so I'm not sure what this bit is. Maybe when you look at it again, you might know what he's talking about here. A line in a plane. Right. If a line lies on a plane, then any 2 points on the line should satisfy the plane equation. Right. Yeah, that makes sense. So, and then if a line's parallel to plane, the dot product to the direction vector and the normal to plane 0. Oh, right. Okay. So this is an important thing. So if we've got a plane here like this, so the direction vector of the line, that was the thing that takes you along the plane. Along the line. So that was if r equals a plus, I'll call it lambda. I think it's normally called lambda actually. Lambda times d, so d for direction. If this line lies along this plane, so another way of saying that is lying, or if it lines parallel to the plane. So let's talk about if a line lays parallel to the plane. So it's not necessarily in the plane, but it lies parallel to it. Then that means that if I take the direction vector and I dot it with the normal, so the normal is the thing that's always 90 degrees to the plane. If these two things are also at 90 degrees, they're parallel. So if d dot that equals 0, and it's parallel, which means that if I can always take some vector away from the line equation to move it onto the plane. Okay, I don't want to get too, oh my god, this topic's so long. I think we're only going to be able to get through, we might not even get through this topic. Look how long it is. I don't think we're going to be able to go into complex numbers today. Is that going to be a problem? Or
No, that's fine.
That's going to be fine. Okay, good, because this topic's absolutely massive. Right, where were we? Oh my gosh, well, I was so far, oh my gosh. Right, it's finding the point of intersection. I can go a bit faster. Are there any bits that haven't made sense I'm doing now? Or do you want me to go slower or faster? Again, we don't have to finish this topic because it is quite a lot. It's a bit like geometric. It's different to all the other maths you're doing.
I'd rather just go at this pace and as far as we can, sort of.
Yeah, okay, because it is complicated. One thing I'm worried about is I don't know if this bit made sense as cross product things. Does any of the bits I've done not make so much sense? Because then we can go back over them.
I don't understand the very first bit of this. So y equals a constant.
Wait. Okay, tell me blah blah blah. Tell me when I'm going past it. Is it this stuff?
I think you've gone past it.
I went past it. Oh, sorry.
It's with plane. So the very first part of.
Oh, the plane thing.
Yeah, I don't get.
Right. Yeah, that's kind of a lot of this is a bit. It's a bit hard to think about. I'll try and draw it. I'll draw a really simple plane. Yeah. Okay. So let's imagine we're looking at it in 2D. Right. So this is an x-axis. This is the y-axis. The z-axis is sort of coming into us. So I draw a little circle around it. That means it's coming into you. It's like an arrow. So you imagine if an arrow looks like this, it's got like feathers and stuff. As in, this is like an actual, like an arching arrow. So if the arrow is going away from you, you see the feathers. So you see a cross. This means a vector is going out of the page. And if you see a dot, that means you can see the end point of the arrow. So it's coming into you. So this means it's coming into you, right? And then I'll draw a plane like this. It's a simple plane. So we're just seeing the plane edge on here. This plane is it's normal to the y-axis. So the y-axis is 90 degrees to it. Again, it's a really simplified plane. So if we want to draw on its normal, we could draw it here. It looks like this. We can draw it anywhere. Doesn't matter where the normal is. It's a unit. It doesn't have to be a unit vector. This one isn't a unit vector. I think normally they are unit vectors. Right. If a point is on this plane, so it's got some position vector like this. If the point is on the plane, then I can redraw the normal down here. That might make it easy for you to see. So here's the normal. If a point's on this plane, then r dot n equals some number. R dot n, remember, when we're talking about projections, the projections, r dot n is this. If n's a unit vector, it's this. It's this length. That's what r dot n is. And if something's on this plane, then it doesn't matter which of these points I choose. When I take r dot n, so this is r1 dot n, this is r2, they have to have the same length in this direction. Otherwise, they're not on the plane. Does that make more sense?
Yeah. Yeah.
Yeah. Okay. Did this stuff make sense? This A dot B thing, being projections and shadows and stuff, because this is kind of a weird thing as well.
No.
Would you want me to try and go over this?
Yeah.
You want me to go over it? It's fine if you do. Honestly, because this topic's absolutely massive. I didn't realize.
That would be good.
Okay, cool. So let's talk about dot products again. Dot products are weird because I just sort of said what they were, and I didn't really explain where they come from. So, dot products. Okay. So, this is what the dot product was. We said the dot product was. Okay, so, right, we figured out what the dot products were for I and J and stuff. So the dot product for I with itself was 1, was the same for J, was the same for K. I just saw the J one in here. We figured that must be true because of the way they were defined, right? Because I was at 90 degrees to J, and that was at 90 degrees to K and all that stuff. So if we put 90 in here, we get 0. So that means that has to be true, and then I dot J has to equal 0. Okay, so that was fine. Then what we said was so A is a vector. We can rewrite that as AX, AY, AZ. That's writing in vector notation, which is the same as writing it like this. So A lots of AX lots of I plus AY lots of J plus AZ lots of K. Okay. What happens if we take A dot with I? Dot with I. Okay, so we use this formula. So the modulus of I is one of the terms, and that just equals 1. Another one of the terms is the modulus of A. Oh, let me also draw what this is. So I've said what it is. I is in this direction. I've just put the two vectors next to each other. A points this way, I points this way. There's some angle between them, which I call theta. Same one as in the equation, cos theta. So A dot I, I've got two equal signs, that's silly. A dot I equals cosine theta, modulus of A, modulus of I, which is 1. So it just equals cosine theta times A. And if we just think to trigonometry and triangles and stuff, so imagine we have a triangle with side length A. I haven't drawn it as a vector, but you could think of it as a vector, and it has some angle theta. Then if we just use our trigonometry, cosine theta equals the adjacent over the hypotenuse. Is that a good way of thinking about it? Yeah, I think that, yeah, it's adjacent. So, we'll just write down what the adjacent is because you don't know. Adj for adjacent, and we'll divide by the hypotenuse. So let's say we're just thinking about we do the vector A, which looks like an arrow. The length of this vector is the modulus of A, right? Just by Pythagoras' theorem. So the cosine of the theta is the adjacent angle divided by the modulus of this vector, which is just the length of this line, which means that the adjacent side is A cosine theta. So when we did A dot I, what we really did is we found the length of this line in the I direction. So when you take dot products, you sort of find the length of a vector in this direction. So A dot I was A cosine theta. That's the length of A along the I direction. So that's what dot products do. They sort of take the shadow of something else. So if you imagine you put like, if you imagine you had a vector, and this is your I direction, and you sort of, oh, I don't want, just ignore that line, and you put the sun above it, then it would make a shadow like this, and the length of that shadow would be A cos theta from using this trigonometric rule. So when we do dot products, that's like taking projections. And then when we start to talk, does that make more sense?
Yeah.
Okay, and that works. It works really well for unit vectors because they have size 1. It gets a little bit more complicated when we talk about other vectors because we have this size here is not equal to 1 in general. But now you can think of dot products as what it does is it takes the projection, which is A cos B, cos theta. So now I'll draw a new one. This is B. So this is A. This is the vector A. This is the vector B. The angle between them is theta. This is A modulus of A cosine theta. That's the length of this line. And now we multiply that by B, so we get a new number, which I'll draw it on like this. And this new number, oh, that does not look good. Wait, I'm gonna get rid of this bit. I hope it doesn't magically draw a line on there. Nope, it didn't do it. Okay, great. So, oh, for goodness sake, never mind. Right, okay, so the length of this line is now A times the length of B times cosine theta. So if B was 1, then that would just be the projection of A cos theta. But now that we have B not being 1, we get, first we project A into the same direction as B, and then we multiply it by how long B is. So that's what a dot product is. Okay, so now if we go back to planes, when we take the dot product between some position vector and the normal, that is the projection of this line in the normal's direction. So it's saying how long is this length? Okay, and for it to be a plane, this length needs to be the same for any vector. So even though the line's getting really long, the further away we go from the origin, the length, this distance is always staying the same, and that defines a plane. So that's why when we, sorry, what was that?
So it will always be 13.
It will always be, well, in this case, it'll always be minus 13, which is saying that.
How is that the case if you've got different values? If you're changing R, but you're not changing, but you're keeping the unit vector constant and the distance constant, how does that work?
Okay, so let's say it was a really, really simple one. Let's say the unit vector is this. No, you won't believe me if I do that. Let me. This is a good question because vectors are so weird. And then we'll write it as A, B, C. All right. I do the dot product. That gets me minus A, minus B, minus C, and that needs to equal. I'll call it a constant. Let's say I increase A by 10. So A changes to A plus 10. So I get minus A minus 10. If I decrease B by 10, I get minus B plus 10 minus C. And that's a constant. So it means that I can't just choose any point. There need to be very, very specific points. But say I move along the x direction by some distance A, that means I need to move along the B direction by some distance. Say I move along the x direction by 10 units. I need to also move along the B direction by minus 10 units, if that makes sense. Does that sort of, because they need to add some value. So if one changes, the other ones need to change in a very specific way, otherwise you're not on the plane anymore. So even though this looks like, oh, you can pick any old R, it doesn't. So say I know one value works. If I then add, say I know A, B, C is on this plane. Sorry, I'll do it down here. So A, B, C, I need to dot that with, was it -4, -5, -1, right? Okay, -1. And that needs to equal -13. So I get -4A, -5B, -C equals -13. I'll rewrite that actually, 4A. So this is the equation for the plane. As long as anytime you take some values, 4 times A plus 5 times B plus C equals 13, that means it's on the plane. So if I now choose a different one, I take A to be, A goes to A plus 1, 4A plus 4, then I can take, I don't know, maybe C goes to C minus 4. So I move, so let me draw it out. This will be, I think this will be the last thing we do, just because otherwise I won't get to my lecture. I'll draw out this vector like this. So one of the points is on the plane, and it has some position A, B, C. B, C. And now say if I move to A plus 1, so A plus 1 is further along in the x direction. Can I write here? Oh, God. Wait, I just want to do this one more time, sorry, just to make sure this, I'll try not to draw so weirdly. Right, so this point. Okay. Right, yeah, so ABC. ABC is on the plane. Now say I increase the A value by 1, so the A was the x direction, so I move out here by 1. Well, then the only way I can keep being on the plane is if my C value goes down by 4. So C needs to go from here maybe to here. So it moves along like this. So I moved to this point, I move into us a little bit, then I move down by 4, so I'm over here, and the B value stays the same, so this value stays the same. And now if I draw the new line, this new point has to be in a very specific place. The plane's actually quite hard to draw here. This plane with this -4, this -5, this -1 is a bit of a weird one. It's easier to think about something like that. But yeah, I hope that makes more sense. Is there any last questions you've got about this plane stuff? Don't be afraid to ask. I do have a little bit of time to. I mean, my lecture's at 4, so I should be fine to get there. But is there anything? Sorry, what was that?
One thing, like, so what exactly, when you were doing R times N equals the distance,
Yep.
What are we actually calculating by doing a vector that's with a point on the plane times the unit vector?
Okay, I think I get what you're saying. Right, so normally when you're used to thinking about equations, you're used to thinking about it by saying like the y value. Oh my God, please. Right, the y value equals m of x plus c, right? So you give me an x value, and then I can tell you what the y value is, right? So say this is my x-axis. Say it doesn't have to be like that, sorry, or it could be f of x. So if you give me an x value, I then tell you the y value by plugging it into this formula, okay? That's called explicit. That's an explicit way of graphing things. So you figure out the y value from the x value explicitly. Another way of thinking about graphing stuff is, let's think about this equation, x squared plus y squared equals 5 squared. Another way of thinking about graphing is, okay, I can rearrange this, and I can get something that y equals 5 squared minus x squared plus or minus. Oh, that looks a bit ugly. That's one way. Sorry, I'll put the 5 here. That's one way I could figure out this answer. Another way I could think about this is I choose a point. Right, this is a really slow process, but it's a way of thinking about how graphs are drawn. So I choose a point, some random point, and if x squared plus y squared equals 5, then I color it in. So I go on my graph, and I choose a random point. I go, this point. Does the x coordinate plus the y coordinate squared equal 5? If no, then I don't color it in. Okay, so this one doesn't. Let me go along to y equals 0 and x equals 5. So 5 squared equals 25 plus 0 squared equals 5 squared, which is 25. Okay, so the point with the point with the point with 5, 0 does work. So I can color that one in. And then I see that if I do that for every single point, the only ones that work are ones that make a circle. So this is called an implicit way. So the value of x implies the value of y through this constraint. So instead of thinking, oh, the y value is some function of the x value, you think, I choose a point, and if it works with this equation, then I get to color it in. And eventually you color in enough points and you see what the function looks like. So that's sort of what this plane equation is like. It's saying that you choose a random point, you choose a random vector, and I do this process to it. And if I get minus 13, I color it in. And then when you do that for all the points in 3D, that colored in region turns out to be a plane.
Okay.
Is that what you're getting at, or does that not make sense?
No, that's fair.
Okay, cool. Yeah, so it is weird. It is really weird. I didn't like implicit equations when I first saw them. I preferred to rearrange things. But when you get the hang of it, when you start thinking about it that way, it does sort of make a bit more sense, I think. Cool. Yeah. So yeah, we didn't quite get through that topic. If you want to let Tom know that we only got to, where did we get to? We sort of did. So we did lots of plane stuff. Finding the equation of a plane. I didn't really know what this was on about. It looked like it was just doing the same things before. This might have been finding the intercept of the plane. I'm not really sure. We got about to here. So we got about to a line in a plane. Finding points of intersection. That sort of. So if you can just let him know that.
Okay.
That'd be good. Okay, cool. I got to shoot now because I've got a lecture.
Yeah.
Okay, cool. All right. Okay. I'll see you guys on Monday. Ta-ra.
Bye. Do you want to let Tom know that we're done? I think I need to lock that.
All right, Tom, we just.
You done? Brilliant. Sorry, I was ready to ask. You can actually end it if you like.
Yeah.